Hey guys, I'm going to talk about the breakdown of one glucose molecule to form ATP and how many ATP are formed from that. Okay, so it's important to understand when we're talking about glucose and the energy that is used from it. Most of the energy created from glucose is used anaerobically or for short bouts of aerobic activity. And the reason for that is the energy of mass from glucose cannot be sustained for long periods of time because of the relatively small amount of ATP that is formed through it. So when we talk about energy used, anaerobic glycolysis generally only releases about 5% of the energy within a glucose molecule. So it's not very high. And then the remaining energy is created when pyruvate converts to acetyl-CoA, and that enters into the citric acid cycle. So that's kind of the process when we're looking at it. Okay, so how does glucose break down to form ATP? When glycolysis starts, 2 ATP are gained from phosphorylation. So if we look at this diagram here, this is where the 2 ATP start. Okay, and then from that, 2 more ATP are formed from acetyl-CoA in the citric acid cycle. So that's down here. So 2 more are converted through the acetyl-CoA. Now, this releases 24 hydrogen atoms, and that helps form more ATP. So then we can break that down as well. So from that, 2 NADH are generated during glycolysis, and this forms 5 ATP. And then 2 NADH are released in the mitochondrion, which is down here through the pyruvate. And now that will form and then pyruvate becomes the acetyl-CoA, and that will form 5 more ATP as well. Okay, so once we get through there, then 6 NADH through the citric acid cycle are released, and this produces 15 ATP, and then 2 FADH in the citric acid cycle produce 3 more ATP. So as we break this all down, through one glucose molecule can form 34 ATP. Okay, and so this chart kind of gives you a breakdown of where they come from. 2 comes from substrate phosphorylation. 5 come through glycolysis and through the 2 NADH, and then 5 more come from pyruvate converting to acetyl-CoA through 2 NADH, and then substrate phosphorylation through the citric acid cycle converts to 2 more ATP, and then 6 NADH through the citric acid cycle will convert to 15 ATP, and then the FADH citric acid cycle converts to 3 more ATP. Okay, so one molecule will yield 34 ATP. Now it's important that we understand that 2 of the ATP molecules were initially phosphorylate with glucose. So there's really only a net of 32 ATP yielded during glucose catabolism in skeletal muscle. All right. Now, as we get into longer bouts of training, aerobic training, and longer durations, we have to look for other energy avenues so that we can sustain training. So what happens after we go through our glucose breakdown, our body will now look for other mechanisms to use for energy systems, and so fatty acid becomes that part of it. Okay, so there's actually kind of a process that it goes through. So the anaerobic reaction of glycolysis accepts glycerol as a 3-phospho-glyceraldehyde as part of that. Okay, so this molecule degrades to pyruvate to form ATP by phosphorylation. So you can see how as we go from glucose, we'll get into glycerol, and then that'll return back into the glycolysis part. Okay, so we need to understand that. And then hydrogen atoms pass on to NAD plus in the citric acid cycle oxidizes pyruvate, and the breakdown of one molecule of glycerol can yield 19 ATP. So we get ATP from glycerol before we even get into the fatty acid side. So we need to understand that. Okay. The gluconeogenic rate of glycerol is important because when glycogen reserves deplete from high intensity training, this is when the aerobic process starts. So that's why it's important to understand that. So now we get into the fatty acid molecule. Okay, and the fatty acid molecule, it will form into acetyl-CoA in the mitochondria during beta oxidation. So fatty acid will go into the mitochondria during and convert into acetyl-CoA during beta oxidation. And then 2 carbon acyl fragments are split from the chain of a fatty acid. So you can see where this goes, it splits in, and then it becomes acetyl-CoA, and that's going to start back into the citric acid cycle. And then ATP phosphorylates the reactions, water is added, hydrogen passes on to become NAD plus and FAD, and the acyl fragments join with coenzyme A to form acetyl-CoA, which we just talked about. Beta oxidation provides the same acetyl unit is generated from glucose catabolism. So as we talked about with glucose and the catabolism that takes place, beta oxidation starts that process on the fatty acid side. And beta oxidation continues until the entire fatty acid molecule degrades to acetyl-CoA from direct entry into the citric acid cycle, which takes place over here. Now, it's important to understand that oxygen must join with hydrogen for beta oxidation process to begin and to break down fatty acid. And fatty acid breakdown directly relates to oxygen consumption. Okay? And during anaerobic conditions and glucose breakdown, hydrogen remains with NAD plus and FAD, halting fat catabolism. So that's where the difference that we use for energy systems when we need to break down either glucose or fatty acid. Now, beta oxidation produces NADH and FADH by connecting the fatty acids molecule into 2 carbon acyl fragments. So we have to understand that first. Okay, so once we do that, then the citric acid cycle will break down the acetyl-CoA into carbon dioxide and hydrogen atoms, which we can see right here. And then that starts through the electron, then the hydrogen oxidizes through the electron transport chain. And that's where more ATP is formed. So this process of fatty acid breakdown, this will yield 147 ATP. And then when we add the 19 more ATP from glycerol, so the total ATP yielded from the fat energy system is 166 ATP. So fat becomes the primary source of energy during exercise recovery when bouts of high intensity, long duration training depletes the glycogen levels. So our body will first go into using glucose as our form of energy, but once we deplete all of that, then the body starts to get into using fats as our primary source of energy. Okay?